Okay, so in this problem, again, as usual, we're going to plug in the infinity and see what we get. So this is very similar to the one we did before, problem number 5. We're going to have 1 going to infinity, and this is an indeterminate form. And so remember that since we have a function being raised to another function, what we want to do is use natural logs to help us figure out what's going on. And so here we're going to call this guy y, and then we're going to remember that e to the natural log of y is equal to y by the properties of logarithms. And so what we're going to find first is the limit as x approaches infinity of natural log of y. And we're going to do this because this is going to allow us to move the exponent down. Okay, so this is equal to the limit as x goes to infinity of natural log, and y is all this stuff inside the purple bubble. So I have 1 plus 8 over x raised to the x over 2. And this one's a little bit less labor intensive than the other one, I think. But what's going to happen is, remember, now this is going to allow us to bring the x over 2 down. So this is equal to the limit as x approaches infinity of x over 2 times natural log of 1 plus 8 over x. Okay, and then notice that what we have is infinity times 0. This whole thing is a natural log of 1, which is 0, which is indeterminate. But remember, to use L'Hopital's rule, we need to have one fraction over another. And so what I do is I grab one of these two factors, and I'm going to write it out as a fraction. So let's say I'm going to move this one down. So what this would equal is the limit as x approaches infinity of natural log of 1 plus 8 over x over 2 over x. And that's this guy that I brought down, and it comes down as the reciprocal. And so notice that if I invert and multiply by this guy, I would go back to this one. And so this is the little trick that I use, because now that I have this guy 0 over the denominator is also approaching 0, this allows me to use L'Hopital's rule. And so then what I would have is the limit as x approaches infinity of, this is kind of a big fraction as well, but the derivative of the numerator is 1 over 1 plus 8 over x times the derivative of the inside. Well, the derivative of the inside is simply, if you bring the x to the top, it would be 8x to the negative 1. So this is going to be negative 8 over x squared. And then the derivative of the bottom is going to be negative 2 over x squared. Okay, and so then let's do a little simplifying here. What I get now is that this is equal to the limit as x goes to infinity of, if I invert and multiply this one, I'm going to get 1 over 1 plus 8 over x times negative 8 over x squared times x squared over negative 2. Okay, and if I simplify, I notice that the x squareds cancel, the negative 2 and the negative 8 reduced to a positive 4 on top. And so what this becomes is the limit as x goes to infinity of 1 over 1 plus 8 over x times 4. And so notice that what happens is this guy, this 8 over x, is approaching 0. And so this limit is equal to positive 4. Because this whole thing is 1 and then 4. But remember that 4 isn't my answer. 4, this number 4, is the limit as x goes to infinity of natural log of y, which is this whole purple guy. And what I really want is the limit as x goes to infinity of y. So my answer is going to be e to this number that I just found, 4. So the answer, then I go back, the answer is going to be e raised to the 4th. And e to the 4th, that's approximately 54.598. 2. And that's it. Okay, so here we have this problem, and I know a lot of you are having trouble with the inverse trig functions and just trig in general. So let's take a little time to review what the arctangent function means. Remember that when you see, for example, arctangent of, let's say, a simple value, let's say 1. Remember that what this is really asking for is, it's saying, well, tangent of what angle is equal to 1? That's the same question that this is asking. So you're asking, okay, 1 is the output. What's the input that gives you that angle? And so, well, you have to remember the unit circle, and remember that tangent is sine over cosine, and the only place where sine and cosine are the same is at when theta is equal to, when the angle is pi over 4. And so the answer to this is pi over 4, and so the answer to this question is pi over 4. So, okay, but this is kind of a more awkward situation. What it's saying is arctangent of, it's asking us for arctangent of, basically arctangent of infinity. Okay, so I mean, if we do the same type of idea here, what it's saying is, okay, tangent of what angle gives me infinity? And so what you have to remember is a little bit about what the tangent function looks like. Remember that the tangent function has vertical asymptotes at negative pi over 2 and pi over 2. And the tangent function looks something like this. Okay, so let's go back to this question. So it's saying tangent of what angle equals infinity? Well, it doesn't really mean equals infinity. It's saying that for what angle is tangent approaching infinity? Okay, so if we look at our graph, well, tangent's going up to infinity right here, and that particular angle is pi over 2. And so this guy is, the answer to this is pi over 2. Okay, so, well, what's going on here is that what this is saying is that this is equal to, so this top part is approaching pi over 2, while the denominator is approaching, well, infinity cubed is going towards infinity, and so notice that what's going on is that we have a constant on the numerator. The bottom's getting bigger and bigger and bigger, so the entire thing is just getting closer and closer to 0. And so really we didn't even need to use L'Hopital's rule at all. And this is one of the things that you have to be careful with, is that if you just start using L'Hopital's rule without actually checking and making sure that you get 0 over 0 or infinity over infinity, then you'll eventually end up in the wrong answer. But this one, we're done. It's 0. Okay, so this problem we have the cube root of x times natural log of x. And as usual, remember, we always plug it in, plug in the value to see where it's going. And this one, what we have is this first one's going to 0, and the second one's going to negative infinity. So this is indeterminate, and by now we probably have a pretty good idea of what to do, because whenever we have 0 times infinity, what we do, or what we've done so far, is we've turned it into a fraction by using our little backwards tortilla trick. So why don't I write, well, this cube root of x, remember this is x to the 1/3. So I'm going to bring this one down. So what I'm going to have is the limit as x goes to 0 from the right. I'm going to leave natural log of x there, and then I'm going to bring x to the negative 1/3 down. If you want, you can write it as 1 over x to the 1/3 as well, but since we're getting the derivative, I might as well just leave it as a negative exponent instead, because it makes the derivative easier to find. So now the numerator is going to negative infinity. This one also is going to infinity, and so I can use L'Hopital's rule now. And so the derivative of the top, well, that's simply 1 over x. The derivative of the bottom, this is negative 1/3 x to the negative 4/3. And I forgot to write the limit again. Limit as x approaches 0 from the right. Sorry about that. Okay, and then if I simplify this, you get limit as x approaches 0 from the right. If I bring it back, why don't I do this? Let me rewrite it as negative 1 over 3x to the 4/3, just to do one extra step for fun. Okay, and then if I do the tortilla, these guys go on top. Let me rewrite the limit again. Limit as x approaches 0 from the right. I have 3x to the 4/3 on top. These guys go on bottom. And this is equal to the limit as x approaches 0 from the right of negative 3x to the 1/3. Because you subtract the exponents, and this is equal to now just 0 by plugging it in. And that's it. We're done.